Welcome to Automated Visual Software Analytics. This part is about module dependencies. We will explain principles of module dependencies and investigate two core types of module dependencies, coupling and cohesion. Let's start with a few principles. Modularization is such a principle. It's a key construction principle for complex software systems. The term module can denote different concepts, for example, subsystems, components, packages, software libraries, classes, or namespaces. So module is a common term for all these different types of units that constitute a complex software system. Modules are typically organized in hierarchies. Now, if you have more than one module, you will have dependencies. Dependencies result from usage relations. For example, if modules include interfaces of other modules. They also result from inheritance relations in object-oriented programming, for example, if modules are subclasses of other classes. In addition, dependency results always if there is any logical dependency or any other kind of relationship between two or more modules. They can be detected by static source code analysis or even by analyzing runtime information. There's a formal way to denote the dependency of a group of modules. This is called dependency network graph. A dependency network graph models dependencies among a collection of modules. And in these graphs, each node represents a module and directed edges represent dependencies. Let's see an example. This is from a C++ software system. It's about the interface header file. And in this graph, we see all include relations from the perspective of the header file interface. So interface includes, for example, string, includes message, includes util, etc. So these relations are so-called direct includes because interface directly requires these interfaces of other classes. Of course, these other classes may have also some dependencies, for example, include relations, and this way we get indirect include dependencies that are also shown in this diagram. It turns out that, for example, some classes like map are directly included and it is also indirectly included. So the whole set of interconnected, interdependent modules are represented by this dependency graph. Now let's define a dependency. A dependency denotes a formal relationship between two modules. Dependencies can be detected by analyzing the source code, for example, by filtering out the include statements or analyzing other kind of static software implementation artifact. They can also be detected by runtime analysis. Let's further define when a module A depends on a module B. For example, if A calls B or any part of B, for example, if B is a header file with different function definitions, with different data type definitions, then if A uses any of these elements, A depends on B, it's called a call dependency. A depends also on B if A inherits from B because A becomes a subclass of B. Or if A uses any variable, for example, a global variable of type B, then we have a kind of data or data type dependency. So these three forms are typical forms of dependencies we have in common programming languages. There's also a a definition for a certain configuration of dependencies. If you have a collection, a set of modules, A1, A2, etc., then this collection is called a clique if for each pair, if you take out two of these modules, if you always have a dependency neglecting the direction of the dependency. So these modules, if this condition holds, if there's always at least one dependencies between two members of the set, then these modules of the set are considered to be closer to each other. So we talk about closeness of modules. We also distinguish between internal and external dependency. Coupling of a module refers to the external dependencies to other modules. That is, coupling represents the degree or even quantifies the degree of intermodule dependency. We can also have a look into one given module. Then we talk about cohesion. Cohesion of a module refers to internal dependencies within the same module. That is, it quantifies the degree of intramodule dependencies. Now, these two core types are distinguished, and we will now go on with coupling. There are different coupling types. We distinguish between afferent coupling, the number of outgoing dependencies to other modules of a given module. Afferent coupling means or represents a measure of how dependent the given module is, dependent from other modules. Afferent coupling, in contrast, represents a number of modules that depend on the given module. So to say, the ingoing dependencies. Afferent coupling serves as a measure of the responsibility that a specific module has with respect to the other modules. Yeah, related to coupling, we have some general design rules. For example, it is considered to be undesired if one module knows internals of another module. So if it's open with respect to its content. Two modules share the same global data is also an undesired design feature. What is desired is if the module has a clear and strict set of dependencies in relation to the other modules. For example, if data is structured, if data is encapsulated, message coupling, or even no coupling. This quality checks here refer to the design of a software system. So if we program a module, we have to keep in mind the coupling quality. And these are just a few examples of what is considered to be useful and less useful if we design a software system, a class, a package, or library. Let's analyze this a little bit further using a bundle view. What you see on the right side is a bundle view. It's a mapping of different files of a software system. And in the middle, we have connections, relations expressed by these banded lines. And in this case, we are looking at afferent coupling relations of the module data. So we ask, where are the modules that data imports or includes? So data includes, for example, data event or data field, data schema, data set, and these other red marked modules. So this is a view on the specific module data, and it shows the afferent couplings of this module. Let's look at afferent couplings, the ingoing coupling. All modules that use, import, or include data. So it's a kind of responsibility view. What kind of responsibility does the module data have? And we're seeing marked in green once again, all these modules that depend on data. So this gives a more or less a first overview of the relations of the coupling of the data module within its context, within the whole system. There are different metrics available that try to measure, to quantify coupling. For example, we have a coupling metric that defines that coupling is measured by a normalized coefficient, and it's 1 minus something, and it takes into account the number of input data parameters, number of input control parameters, the same for output data and output control parameters, and even global variables, and the number of modules called, it's known by the term fan-out, and the number of modules calling the module under consideration, the so-called fan-in number. So if we look at this formula, we see a metric measurement will be in the range between 0 and 1. And if you have a large number of parameters, now unsharply speaking, if you have a large number of parameters, then you have a strong coupling, yeah, because this second term tends to be 0, and so we get a high coupling measure. So if C goes towards 1, we speak about a strong coupling because many parameters are involved, whereas a coupling that goes towards zeros represents a weak coupling. A common characteristic of coupling metrics is that they sometimes work with certain empirically determined values. For example, A, B, C are weights, and there is more weight given. If we look at the coefficients here, A, B, and C, there's more weight given to control parameters, and K is defined to be 1. There are sometimes different constants, different values around in literature. So be aware that coupling metric is a field where sometimes strong empirical observations play a role. So don't expect to have a sharp metric value here, but it's in general an indication. And so this, its original purpose, its true purpose is to give indications about coupling. Yeah, let's consider one example, 3 classes, and we are now talking about the coupling of the rectangle class. It's a class diagram, and for example, we have as number of input parameters 2. This comes from using vector 2D here 2 times. We have a fan out of 1 and a fan in of 1 related to these 2 classes. One uses vector, rectangle uses vector, and plot uses rectangle. And the coupling metric value would result to this value here just by putting in the values in the formula. So we have a relatively strong coupling, not too strong, but it's not weak, let's say. Now, what about cohesion? We have seen coupling refers to the intermodule dependencies, the dependencies between classes, for example. Cohesion has a different perspective. It looks into inside one module and asks, what about the internal relationships inside a module? We also distinguish between afferent cohesion, the number of dependencies within a module, and afferent cohesion, the number of responsibilities within a module. There are also, once again, certain design rules, or at least design patterns. For example, it is considered to be undesired if elements within a module are arbitrarily grouped or have different nature but belong to a similar category. It is considered to be more useful if we have inside a module shared inputs and outputs and pipelines, contribution to a single well-defined task. Yes, this is an ultimate design goal. If we have a single well-defined task, this leads to a strong cohesion inside a module. Cohesion will be investigated in more detail if we look at object-oriented metrics. So let's evaluate the findings so far. We have talked about coupling and cohesion, and we can use coupling and cohesion as indicators. What do they indicate? A high degree of efferent coupling can indicate that a module is unfocused. It may also indicate brittleness, since a module depends on the stability of many coupled modules. A high degree of coupling, in general, can indicate higher costs for reuse and maintenance of the module. Although dependency is some natural consequence of organizing a complex system in a hierarchic way, but on the other side, dependencies may lead, and typically do lead, to higher costs in maintenance if you have an extremely high coupling in your system, because everything depends on everything, for example. A low degree of cohesion inside a module can indicate that some module parts are not related to each other. Possibly, these unrelated parts should be refactored, redistributed, or redesigned. A high degree of cohesion generally indicates that the module's parts are interrelated and hence form a strong module. A tight bundling of attributes and methods in a class, for example, is such a case where you have a high degree of cohesion. Yeah, this more or less outlines how cohesion can be used to get a first view on a specific situation in a complex software system. Yeah, let's summarize the findings of this part. The implementation of a complex computer-based system is generally characterized by modularization. The way modules depend are represented by the dependency network graph, which reveals the dependencies among modules in a formal way. Typically, dependencies are determined by static code analysis. This is the most used way to detect dependencies. Intermodule and intramodule dependency measures, coupling and cohesion, reflect to different aspects the quality of the dependencies. Coupling indicates the quality of modularization, whereas cohesion gives indications about the composition of a module. Software analytics, both aspects support program understanding and comprehension. So if you want to understand and comprehend a specific given setting in a complex software system, coupling is one first way to understand how the system works and how it is composed. Dependency network graphs can also be used for prediction analytics. So they play a certain role in prediction analytics. For example, if we want to assess the likelihood for bug propagation, efforts for redesign or refactoring, then we go back to the network dependency network graph in order to find out which modules are closer to each other. So this concludes this part about module dependencies. We have introduced some terminology. Dependency, for example. Dependency denotes a relationship between two modules inferred from data dependencies, call dependencies, or inheritance dependencies. Coupling refers to the manner and degree of interdependence between software modules, whereas cohesion refers to the manner and degree to which the tasks performed by a single software module are related to one another. Yeah, as further reading, I can recommend, for example, Software Engineering, a Practitioner's Approach, or Towards a Metrics Suite for Object-Oriented Design, focusing on coupling and cohesion issues in object-oriented systems. Let's end with a few remarks. Yeah, the actual dependencies may be more complex compared to those detected by static source code analysis. Give you one example. Pure virtual methods or calls via function pointers are generally resolved at runtime. That is, they are not detectable at all by static source code analysis. So to detect those dependencies, runtime behavior has to be analyzed, for example, by recording a trace or by analyzing the function usage for a given use case or for a given test case. Unexpected cliques of modules often indicate and suggest abstraction, for example, to build a new package, class, or library. So if you have cliques, think about it, and this may indicate that these modules are very close, but maybe too close. Dependencies to standard modules, such as system libraries, frequently can be excluded for analysis or even be ignored, because these modules can be considered to be part of the given and defined programming environment. Dependency metrics also reflect source code complexity that is induced by the use of other modules, for example, due to calls, data usage, or inheritance relationships. For that reason, it is a key indicator for redesign, refactoring, repackaging, and provides base information for software analytics.